In this video, I'd like to walk through some derivatives. Some of these problems that we'll walk through are more theoretical and an application, but most of them will be evaluating derivatives. Let's start with the definition of a derivative. The derivative of the function x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. We know this as the difference quotient. And if we're given the function x squared minus 2x plus 7, and we want to use this difference quotient to find the derivative of the function f of x, then here's an approach that works really well. What I need to do is take f of x plus h, so I'm going to, in place of x, put x plus h. So I have x squared minus 2x plus 7. So here's the x squared minus 2x, and in place of x, I put x plus h plus 7. When I work that out, I meant to leave that top one blank, I think, so that you can see the progression. So let me erase that top one. So as you look back on this, you can see the progression of what we did. So when I do this problem, I think of these empty parentheses, and I put those in place of each x. So we have x squared minus 2x, and here's our x, plus 7. And in place of x, I'm going to put the x plus h. It's sometimes going to be beneficial to evaluate that piece before we go any further. So let's look at f of x plus h. X plus h, quantity squared. I could use a pattern to see that that's x squared plus 2xh plus h squared. If you're not sure what I'm doing there, then go ahead and FOIL x plus h, but you'll see that it's equivalent to the first term squared plus twice the product of the two pieces, x and h, plus the second term squared, the h squared. So I get x squared plus 2xh plus h squared. Now I need to distribute a -2 to the x. So we have -2x. And watch what happens next. -2 times h. This is a common error here, is to sometimes lose this negative. So maybe look closely at this negative. The negative in front of the 2 is distributing to the x and the h. So it's -2 times x, -2 times h. And then the last piece we have here is plus 7. What I'm going to do is then write, I'll use another color, this blue. I'm going to then write the subtraction of f of x. So I'm going to subtract x squared. I'm going to subtract -2x, but do you see that that's the same as adding 2x? And I'm going to subtract 7. So what happens is the x squared term cancels, -2x plus 2x cancels, 7 minus 7 cancels, and we're left with 2xh plus h squared minus 2h. So going back to f prime of x, that's equal to the limit. Don't lose this limit. We're not just doing a difference quotient, we're doing the limit of this difference quotient. And this numerator we have worked out to be 2xh plus h squared minus 2h. And then we're going to put the whole thing over h. When I divide the h, I get the limit as h approaches 0. 2x divided by h is 2x. H squared divided by h is h, and -2 divided by h is -2. So I have the limit as h approaches 0 of 2x plus h minus 2. And by direct substitution, that's going to be 2x plus 0, because I'm going to let h approach 0, minus 2, or 2x minus 2. It's the final answer. Now you may know how to do a derivative with the power rule, and we could see that it's 2x minus 2, 2 times 1, and then x to the 2 minus 1, and then negative 2 times 1 times x to the 0 would give us the 2x minus 2 using the power rule also. So I could use that to check the answer, but if the directions specify to use the difference quotient to find the derivative, then we would want to use this whole piece. Now this next example is going to ask us to sketch the graph of a non-constant function with each of these properties that are listed. If you'll ignore the numbering I have here, the numbering is for a particular class, but if you're watching this video and you're not in that particular class, just ignore that numbering. But what we want to do is sketch a graph of a non-constant function that has each of these characteristics. So let's start with the limit as x approaches 5 from the right is 8. Or actually, you know what? I said we're going to start there, but let's start with the easy part. This purple, f of negative 5 is 3. F of negative 2 is 3. F of 5 is 3. So we're done with this. And let's do f of negative 1 is pi. So that's going to be somewhere above the 3, right? So we have these pieces done. And now let's go back to that blue limit as x approaches 5 from the left is negative 8. So here's 5 as I'm approaching, oh, and you know, I can see that I misplaced this f of 5. I don't know why I did that, but let's check the others. F of negative 5 is 3, f of negative 2 is 3, and f of positive 5 is 3. Okay, but as we're getting closer and closer to 5 from the right, we're going to approach 8. So it doesn't matter what direction we come from, and we can do all kinds of crazy things here, right? Could be a straight line. What it can't be, if we don't want it to be constant at any point, is we don't want a line like this, right? If we're saying that it's not constant at any point. But this demonstrates that the limit as x approaches 5 from the right is 8. So as I'm coming in towards 5 from the right, so as we're getting closer and closer to 5 from the right, the function's value is getting closer and closer to 8. Next, this green piece, the limit as x approaches 5 from the left is negative 8. So I'll go down here to negative 8. And as we get closer and closer here, we're going to be at negative 8. So somehow I want to connect this green to this orange, but we'll wait to do that because we have one last piece to include in our graph, and that's this first derivative at negative 1 is 0. So what you may remember from the reading is that the graph of that gives us either something like that, and here the tangent is 0, so the first derivative is 0, or something like this where we can see that the slope is 0 or the first derivative is 0. We could make this either way. It seems kind of natural that I could make it easily like this. So now I'll do that and I'll connect. Doesn't matter what happens in between as long as I get here. Now I need to connect these two purple points, but without making it constant. I'll just go like that. There are an infinite number of answers. And now a good form is to then fill out the rest of the graph. So somehow I've got to draw something in for this -10 up to -5. How about if I just do that? And that settles it. So this graph meets all of the criteria that's listed. Let's run through each one. Let me turn on the highlighter here. We've got that the limit as x approaches 5 from the right is approaching 8. We've got the limit as x approaches 5 from the left is getting closer to, the function is getting closer to -8. Doesn't actually equal -8, and that's why we've got an open circle here, but it's getting closer. The value of the function when x is -5 is 3. When x is -2, it's 3. When x is +5, it's 3. The value of the function when x is -1 is equal to pi. And then this derivative at -1 is 0. The slope of the line tangent at that point is 0. And that does it. That gives us the graph with each of those different characteristics. This next example that you see partially worked out says determine the equation of a line that's tangent to this curve. We want the equation of a line tangent to f of x at the point 9, 12. Oh, sorry about that. The page disappeared. So what we're doing is determining the equation of the tangent line to the curve f of x at the point 9, 12. The first step is to think, what do I need to know in order to have the equation of a line? Well, I need an m and a b, and then I would have my y equals mx plus b. I'd have everything I need for y equals mx plus b. The first step is to find m, the tangent. The slope of the line that's tangent to this derivative, or I'm sorry, to this function, is the derivative. So if I do the derivative of f of x, I'd get 2 over the square root of x. And that's an equation I can use to find the slope of the tangent line. Well, I want the slope at this point where x equals 9. So that's find the derivative of the function at x equals 9. So in other words, I'm going to take this 2 over the square root of x and replace the x with 9. 2 over the square root of 9 is 2/3. So I can see that the slope of this tangent line is 2/3. Once I have that 2/3, I can use the slope-intercept form, y equals mx plus b, replace the y with 9, replace the slope with 2/3. Oh, I just saw it. I don't know if you see this. I wrote this quickly earlier. Glad I'm catching it now. But I can replace the y, not with 9. Oops. Sorry about that. The pen's going a little crazy here, right? And I want to replace the y, of course, with 12 because we have x equals 9 when y is 12 because we have an ordered pair. So y equals 12. The slope is 2/3. And x equals 9. Now I can plug this 12, 2/3, and 9 in. Y is 12, so y equals 2/3. X is 9, so 2/3 of 9 plus b. And when I solve that equation, it'll give me b, and I can put that y-intercept, or that b, in here so that I'd have y equals 2/3 x plus whatever b is. I'm going to leave that last algebra step for you. One more example here. Write an equation that expresses the fact that a function is continuous at the number a equals 109. The definition of continuity of a function at a point a f of a gives us this, that the limit as x approaches a of the function f of x is equal to the value of the function at a. In other words, the value of the function at a, and if the point we're using is 109, then the value of the function at 109 is f of 109. And that has to be equivalent to the limit of f of x as x approaches 109. This demonstrates that I know the definition of continuous. Let's jump into some examples of derivatives. This first example is using implicit differentiation. So off to the side, before we start, let's do a little bit of legwork and remember the derivative of x with respect to x. Derivative of x with respect to x is 1, right? The derivative of y with respect to x, we're going to use y prime as another symbol for the derivative of y with respect to x. Now, what's the derivative of x to the fifth with respect to x? Just applying the power rule, we get 5x to the fourth. We could say, if we wanted to apply the chain rule, that we then have to go back and do the derivative of x, right? The derivative of x with respect to x is just 1. So I get 5x to the 4th. So I don't really need to do the chaining because it's the derivative of x with respect to x, but I could do that chaining and I would simply get a 1. The derivative of 6y with respect to x. To start with, the derivative of 6 times a variable is 6. But then I have to do times the derivative of y with respect to x. So I'm going to write that 6y prime. That's the piece that many students tend to forget. When we're doing the derivative of 6y with respect to x, when these don't match, I have to apply the chain rule. I have to show that that's times the derivative of y with respect to x, which is not a 1, so I do need to write it. And the easier, more simplified way of writing it is y prime. Last here, we've got the derivative of pi. Don't be fooled by that pi. It's just a constant, and the derivative of a constant is 0. So let's apply that to our example. The derivative, if we're doing the implicit differentiation, what we're going to do is the derivative with respect to x of each of these pieces, right? So the derivative of x to the fifth with respect to x is 5x to the 4 times the derivative of x with respect to x, but that's just 1, plus 6 times the derivative of y with respect to x. So I'm going to write that as a y prime equals the derivative of 2x to the fifth. 2 times 5 is 10, x to the 4th. Let me be a little more consistent with the coloring here. Plus the derivative of 3y to the 4th. Now be careful here. Remember, I'm going to have to chain. So 3 times 4 is 12, 12y cubed times the derivative of y with respect to x, so y prime, plus the derivative of pi, since pi is a constant, is just 0. The next step to find the derivative of y, in other words, find y prime, the next step is going to be to isolate these y prime terms. I'm going to do that in 2 steps. You could easily, many of you could easily do this in 1 step, and that's okay. I'm going to go ahead and do it in 2 steps. So I'm going to subtract 5x to the 4th from both sides. I'm going to subtract 12y cubed y prime from both sides. Now I'm doing that so that I can move this 5x to the 4th over to the other side, and I can move this 12y cubed y prime to the other side. So it would look like this. For y prime terms, I have y prime times 6, and then from the other side, when I move this 12y cubed y prime over, I've got minus 12y cubed y prime. I'm going to put the y prime up in front in both of those. You might see why in just a minute. And this is the extra step that you might not always show. And this is equal to this 10x to the 4th minus 5x to the 4th. Do you see why I wrote this the way I did? Because the next thing I'm thinking of is factoring out the y prime. When I factor out the y prime, I have 6 minus 12y cubed. So y prime is 10x to the 4th minus 5x to the 4th over 6 minus 12y cubed. But wait, there's more. Do you see that we could simplify this? This 10x to the 4th minus 5x to the 4th. We have like terms. 10 minus 5 is 5. So we have 5x to the 4th. And then I could factor a 6 from the 6 in the 12y cubed, but it's not necessary because it's not going to reduce with the 5. So you could either factor it or you could leave it unfactored. But this is the final answer here. Let me erase some of this and just go back because a lot of students struggle with some of this. I want to show you this one more time. Okay, I've erased some of that work, and now I'm going to do this one more time, but going all the way through to see if you can follow. We'd start with the derivative of x to the 5th, so that's 5x to the 4th. The derivative of 6y is going to be 6 times the derivative of y equals 2 times 5 is 10, x to the 5 minus 1 is 4, plus 3 times 4 is 12, y cubed, times the derivative of y, I always have to chain, plus the derivative of pi is just 0. Solving for y prime, I can put the y prime terms on the left, so I have a 6, and then I'm going to subtract this 12y cubed y prime from both sides. So those are the two y prime terms. And then that's equal to, we have our 10x to the 4th and subtract 5x to the 4th. You might notice that this 10x to the 4th minus 5x to the 4th could be simplified. 10 minus 5 is 5, so 5x to the 4th. And then I'm going to divide by the 6 minus 12y cubed so that I have the y prime isolated. Well, I hope you found this short video helpful. Stay tuned for part 2 if you'd like to see a few more derivatives worked out.